My name is Monty Elmore. I'm here from the Pacific Northwest National Laboratory. That's in Richland, Washington. It's mostly a Department of Energy laboratory. And Jennifer Hamilton here from the California Fuel Cell Partnership in Sacramento, California. She'll be doing actually most of the presentation for us. The project is to demonstrate this fuel cell powered container that would replace a diesel generator set on barges. And that's what we're here for, is to provide information on that, some safety training like for the fire department, for first responders, and just some highlights of safety features and things like that on the container. So that's what you'll be hearing this morning. And with that, I'll turn it over to Jennifer Hamilton then.
So I'm Jennifer Hamilton with the California Fuel Cell Partnership, and has anybody heard of us ever? Yeah, have you? Good. Well, we have a couple of gentlemen here from the Servco Toyota dealership, and Toyota is a member of the Fuel Cell Partnership along with other automakers that are all working on hydrogen fuel cell vehicles. And so I was here a few years ago with Monty and a flame prop vehicle to do training with the fire department in relation to passenger vehicles. But today we're going to talk about what you're going to see up here, which is a maritime application for hydrogen and fuel cells. And personally, I think it's pretty exciting. It's a new application, and I think this is a great opportunity. So I'm contracted to come and deliver the training. So we'll begin with some high-level overview stuff, and this does get into more detail in the next set of slides after this. So I know this will probably raise questions, but please hold them, and we will get into some more detail. Okay, so what are we doing and why? What is happening is that a fuel cell unit will replace the diesel unit in an ISO container that the reefers will be able to plug into. So the hydrogen will provide fuel to the fuel cell, which will generate the electricity to power the reefers. And this is a demonstration project, and there will be data collected. This is a 100 kilowatt system in a 20-foot container. Deployment is for 6 months, both on land and at sea. And there are a strategic set of partners here that are encompassing both the hydrogen fuel cell area as well as the maritime communities. So this is a learning project. Where we are in this project is to build the unit, which is in development now. We've been getting some photos from the developer, and that will be arriving in late May, early June. So while Sandia is the project lead on this, Sandia National Laboratory, it's funded by the U.S. Department of Energy, and Sandia has contracted with a company out of Vancouver called Hydrogenics, and they are a fuel cell supplier, and their fuel cells are in this unit, and then they have acquired the other components to put into the unit. And so they will be doing, after it gets done being built, they'll be doing some validation testing at their lab before they ship it here, and it'll go through a commissioning process, and there will be further training from Hydrogenics to the users here at Young Brothers. So they'll get this initial training, and then they'll get some hands-on training. I'd like to acknowledge all of the partners in this project, and as I mentioned, it includes the U.S. Department of Energy. Hydrogenics is the project, or the putting together the unit. Young Brothers and FOSS, of course, with some other maritime, ABS, and Coast Guard. Thank you for coming. Some other partners include the Hawaii Center for Advanced Transportation Technologies. HCAT is operating the station at Hickam, and that's where the fuel will be coming from, as well as Hawaii Natural Energy Institute as a partner. And of course, again, the National Lab is the project lead. So there's a number of reasons why this project is moving forward. For technology reasons, we want to test and refine it for a maritime application. As you'll see in the presentation, there are many applications for hydrogen and fuel cells, and this is yet another. And as I mentioned, I think it's an exciting opportunity. Regulatory reasons to enable future hydrogen fuel cell maritime use. So again, data will be collected and learnings, if you will, and applied to further deployment for future units to be used in maritime. Environmental reasons to reduce pollutant and greenhouse gas emissions. Fuel cells are zero emission at the point of use. The only byproduct is water and heat. So you do get that immediate zero emission element there. And then finally, economic reasons. There's a real potential for this to be competitive with diesel or even maybe more cost effective. And it also is developing a new market for fuel cells. So there's quite a few different areas for doing this. In relation to the emissions, this graph is demonstrating since 1996 the changes in emissions requirements for diesel and how that cost increases moving through the stages. So to get down here to this ultimate goal requires about 30% of the total cost of the generator set for diesel. And if you go directly to fuel cells, you get to that zero emission right away without having to make that transition. So that is an advantage. In terms of fuel cost, the potential is there for hydrogen to be on par, if not a little bit better in cost than diesel. Right now, it's not the case, but there's definitely potential. So that's the main drive from this slide. In terms of where we'd like to see this go, right now we're in small demonstrations, right? We have one unit that we're deploying and there's many, many diesel units out there. But we'd like to ultimately get to large commercial deployment, both on dockside and for the barge and vessel. So big picture, larger deployment, and that's the ultimate goal. And over here, you see we're at 100 kilowatt fuel cell for this deployment. This is less than 200 and then over 1 megawatt, so really scaling up in the power generation as well. In terms of the codes and standards, while they don't really exist for hydrogen and fuel cells in maritime at this point, there's also work being done and collaboration being done between the project developers and the maritime folks to work with the existing standards for hydrogen and fuel cells that exist for vehicles and stationary and portable applications and the existing maritime safety requirements and develop those codes and standards. So that's another learning aspect from this project. This is a nice comment from the US Coast Guard that is thanking these folks for the efforts to bring the renewable energy source to the maritime sector. So I think that's a nice statement for the project moving forward. In terms of the sort of bigger picture, there's benefits that are on a global, national, and then down to the local scale. So if you've heard the term think globally, act locally, I think that applies here. This slide was borrowed from the HNEI and who work very diligently in Hawaii to bring hydrogen and fuel cells and infrastructure. And there's a lot of opportunity in Hawaii for making hydrogen from renewable source and providing a local energy source. And so that kind of translates into some energy independence. So let's get to the high level of the use and handling considerations. In terms of how this will look, it will be the same type of container and look essentially like the genset. The difference is that rather than using diesel fuel and internal combustion, it's using hydrogen, compressed gaseous hydrogen stored on board, and a fuel cell to generate the electricity. So basically replacing this component here with these components and still plugging the reefers in as normal. There is also a benefit in that it's much quieter than the diesel, and of course the zero emissions. If there were fire, then the tanks need to vent because it's pressurized gas, and as the tanks heat up, the pressure rises, so we need to vent that. And there are vents located here that will vent the contents of the hydrogen storage, which is in this area here. And they're in a location that facilitates venting up and away. And we'll talk about the properties of hydrogen, but suffice it to say it's much lighter than air and it wants to rise and dissipate anyway, so this helps to facilitate that. And that's really why there needs to be a release. The only other thing that is a remote possibility is if there's a failure of the safety valves, and that is actually a very, very small chance. And this number of once in 5+ years comes from a very large database that has encompassed many years of data acquisition from many different types of use and different sorts of valves and so forth. It's a national database, and if you really want access to it, I'm sure I can get you to it. But that's a very small likelihood. And I will say that To my knowledge, from what I know in working with the vehicles, these components are designed to standards and they are tested at the component level as well as at the system level. So the chance of this happening is really not very likely. So this project went to also the Hydrogen Safety Panel, which is through the Pacific Northwest National Laboratory. It's a panel of folks who have over collectively hundreds of years of experience with hydrogen and safety. Through the work with the FMEA and through the safety panel, they've decided to take this extra precaution, just indicating this zone of where a hydrogen release would occur, and that you probably don't want to have any continuous work in that area. So you'll see here it's extends out to about 45 feet out and about 60 feet up from the top of the container. And this is just a diagram with a diesel container, but showing the relative area of what they're talking about. So they indicate transit is okay, but if there's a fire in or around the container, you want to avoid this area. And if continuous work needs to be done within the zone, they recommend reorienting the generator. The fuel cells themselves need oxygen from the air in order to function, so they use hydrogen from the tank and oxygen from the air to generate electricity. So there does need to be some clearance in the air intake, which is this vent here. And so the recommendation is the 2-foot clearance on that side in terms of the handling for those that will be moving these around and stacking things around it. The vents, and you'll see this diagram again, but the vents will be clearly indicated with some bright colored tape or paint. And again, the hydrogen vents are at this end. So this is a demonstration of the way that the clearance here of the 2 feet. Don't want to be smooshing it together. Now, it's not a dangerous situation. It's just that the fuel cell wouldn't be able to function properly and it would likely shut down, but it wouldn't be a hazard per se. So the 2-foot clearance on either side. The hydrogen relief vent pointed outward and away. The recommendation is also to top pick these containers and not forklift them. It's not a requirement, but that's the recommendation from the manufacturer. And although it's not required, they are following hazmat segregation for this unit. So it's another precaution. So again, recommend the top picking. They're indicating here to try to prevent any damage from forklift. In terms of the user interface, this is the primary and really the only place where the user needs to interface with the unit, and that's at the opposite end from the hydrogen storage. There are 10 reefer plugs. There is 2 sets of start-stop, one for the system run-stop, so basically turning it on and off, and one for a system leak check. If the system is all good and everything's running, this green light will be in a solid state, green. And if there are faults, they'll be indicated by this red light, and we'll go through that in more detail later. And suffice it to say right now that the generator has redundant and numerous safety systems to mitigate issues and to let the user know that something's wrong. And ultimately, the unit's designed to shut itself off if there are problems. If someone needs to, there's also an emergency stop at the user interface. So if they really feel like something's wrong, they can hit that stop and it completely powers down the whole unit. In terms of notification procedures for the Young Brothers personnel, if an audible alarm is sounding, that means the generator has detected a potentially hazardous leak and has shut down. What that means is the fuel has been isolated to those storage tanks. And we'll talk more about what those storage tanks are like. Very loud hissing is an indication that you probably have a pretty good leak going on. There are gas sensors that will detect hydrogen leaks, but if you hear that hissing, you probably want, the unit should pick that up and may want to, you could hit the e-stop if you feel there's a problem. The red light, if the status is lit but it has no alarm, then the generator's detected something's wrong, but it's not necessarily a hazardous condition, but it will have stopped. And if the unit doesn't seem to be producing power, then check those generator status lights. For any exceptions or concerns for the Young Brothers folks using this, please make notification via your immediate supervisor and Gavin. He's the port engineer barges. The highlight here is that basically the generator is constantly monitoring itself. And really, there's no need for an operator to have to enter into the generator room or do anything beside check that little user panel. to see what's happening, and that would be indications through the lights there. For refueling, initially the unit will be trucked, seems to be the plan right now, the unit will be trucked off-site to Hickam Air Force Base and fueled there. And there are plans for construction of a trailer, a mobile fueling unit, which would be filled at Hickam and then brought on site. Those of you with young brothers, the training plans are that this initial training is for management and supervisory personnel. In May, they'll be at the monthly safety meeting. The managers will cover the training with designated shoreside and marine operations and maintenance employees. Then after the generator arrives, and that's in the late May to early June timeframe, there's additional operator training from the provider, Hydrogenics. And select employees will be notified on who needs to get that additional information. And any machine operator or other employee who has not received this training should not be allowed to operate or move or have interaction with the unit. And Young Brothers will be tracking the safety training records for everyone, and managers and superintendents should plan accordingly. So that concludes the overview for Young Brothers personnel. And what we'll do next, welcome, Fire. Thanks for showing up, and thanks for your time. So we'll start in with a presentation that, again, will cover some of the same, but get into some more detail as far as the operation, and then we will go outside to look at a flame prop that has been brought to us by Blue Planet over on the Big Island, and we'll come back in and talk about emergency response. So this set of slides has actually been adapted from a national hydrogen and fuel cells emergency response training resource that was recently developed by us at the California Fuel Cell Partnership and the Pacific Northwest National Lab and the U.S. Department of Energy. This resource is available on a website called h2tools.org, hydrogentools.org. And there's a lot of other good resources on there, so please check that out, if you would. So we've adapted this training specifically for this project. As I said, at the Fuel Cell Partnership, we are normally delivering information on light-duty passenger vehicles and transit buses that use hydrogen and fuel cells. But this application is also using hydrogen and fuel cells, so we've adapted it. So we were here to talk about hydrogen fuel cell vehicles, and we had this Chevrolet Equinox fuel cell vehicle. There are about 5 of these still being operated at Hickam and fueling there. But there are a number of other vehicles, and some of those are actually being leased in California to customers and have been for a couple years, including the Hyundai, the Honda FCX Clarity, the Mercedes-Benz B-Class F-Cell, and the Toyota has announced their Mirai, which will be for sale later in California later this year. So just to give you a little bit of perspective, while this Maritime application is a new application and a demonstration, hydrogen and fuel cell application for vehicles has been going on for about the last 15 years, and in California that's being driven by legislation. So the governor's office is very involved, the Air Resources Board, and the Energy Commission in co-funding infrastructure. And what we've learned through the years is that the stations need to come first for people to buy the technology. So for our friends at Servco, getting a station in and having a reliable place for people to get fuel will certainly help with the interest in buying the vehicle. On a national level, there's been a fairly recent development of an organization called H2 USA. And this is a public-private partnership which includes entities from Hawaii, the Hydrogen Natural Energy Institute, the federal government, of course, automakers, so you see that there's a large collaboration, and that is, again, on a national scale. On an international scale, there are also public-private partnerships taking place and lots of collaboration between the US and the European countries. This is just an example of some of the activity. In Germany, they have quite an aggressive plan moving forward. All these dots are plans for hydrogen stations in Germany. In talking with Stan from HCAT, which is the Hydrogen Center for Advanced Transportation Technology, he was saying, you know, in Hawaii, we could really have a good network on this island with just a few stations. In California, we've decided that 68 really need to be where we even start to have enough stations to get people to and from where they need to go and confident in fueling. On this island, there could just be a handful, and that's, I think, an advantage. And finally, in Japan, the Mirai is Toyota, and they are very ambitious in getting their fueling station network put in, and they just opened 17 new fueling stations at the end of March. So just an idea of what's happening kind of in every other part of the world. And here on Hawaii, there's other emphasis and application for hydrogen and fuel cells, but the Maritime is definitely the newest and exciting. So I'm going to show you this video from Toyota about the Mirai.
Today, we're at a turning point in automobile history. A turning point where people will embrace a new environmentally friendly car that is a pleasure to drive. A turning point where a four-door sedan can travel 300 miles on a single tank of hydrogen, can be refueled in under 5 minutes, and emit only water vapor. A turning point that represents many years and countless hours of work by our team to create a car that redefines the industry. All of us at Toyota believe in a future that will be safer, greener, and easier for everyone. We imagine a world filled with vehicles that will diminish our dependence on oil and reduce harm to the environment. A bold but inspiring goal, and today it is a reality. Our fuel cell vehicle runs on hydrogen that can be made from virtually anything, even garbage. It has a fuel cell that creates enough electricity to power a house for about a week. This is a car that lets you have it all with no compromises. As a test driver, I knew this new fuel cell vehicle had to be truly fun to drive, and believe me, it is. It has a low center of gravity, which gives it very dynamic handling. After surviving millions of miles on a test track and 10 years of testing on public roads in freezing cold and scorching heat, after passing extensive crash tests, and after working with local governments and researchers around the world to help make sure it is easy and convenient to refuel, we're ready to deliver. The name we've given to our new car is Mirai, which in Japanese means future. We believe that behind the wheel of the Mirai, we can go places we have never been, to a world that is better, in a car that is better. For us, this isn't just another car. This is an opportunity to really make a difference. And making a difference is what Toyota is all about. The future has arrived, and it's called Mirai.
Give you some perspective and kind of what's happening even here in Hawaii, because Servco is building a fueling station and will have some Mirai vehicles and hopefully be selling those relatively soon. So in terms of other applications, not only maritime, there's portable personal power, there's larger stationary power, there's backup power for cell phone towers. This is fuel cell trolleys that are active in Aruba and Dubai. Fuel cell forklifts are pretty popular. There's advantages there from battery in that you don't have to have a place to store battery packs or recharge them. The fueling only takes a couple minutes, and they get ample runtime off of one fill of hydrogen. So, and the operators can fill it easily. Also, just for some perspective, behind the curtain in the codes and standards world, which I also participate in, there's a lot of activity in many different areas of hydrogen and fuel cells. And of course, Maritime is one of the new ones, and developing those codes and standards. From anything from generators to portable, stationary, and so forth. So for this project, again, the project scope is to design, build, and deploy the 100 kilowatt fuel cell system, which replaces the diesel generator system. So it's doing the same thing in that it's powering the reefers, but it's doing it with hydrogen and a fuel cell. Again, a 6-month deployment on land and over the sea. The procedures for safety, operation, and regulation are all in development. So this is a data gathering exercise. It is a prototype, if you will. And also to demonstrate affordability and accessibility of hydrogen. Our project lead, Joe Pratt from Sandia National Laboratory, will be presenting on this at the Department of Energy's annual merit review for, it's basically for the hydrogen program and advanced vehicle technologies, all of the projects that your tax money funds. Anybody can go to it. You can sit in and hear about the projects. So just again to highlight some of the major points of the project overview, this unit is the first to be deployed on land in a shipping port in Hawaii. So this is novel. After an evaluation period, it'll be deployed on unmanned barges, making trips between the islands. The total deployment period is 6 months, and a maximum of 10 units can be plugged into the unit. With, as we discussed a moment ago, enough hydrogen to support a round trip between the islands, and NAMI indicated about 200 hours of operation per fill. So let's do some more kind of overview for fuel cells and hydrogen. Hydrogen as a fuel has been made for decades. We make it right now from steam methane reforming of natural gas, mostly. It can be made from a variety of resources. Again, local resources, which promotes energy independence and a local energy source. It can also be made from renewables and almost zero emission. Fuel cells, there's a variety of types of fuel cells. The kind that we're talking about today is a PEM, electrolyte fuel cell, and that's what's used for transportation. There's other types used for stationary and portable power. Overall, there's a wide deployment of hydrogen in fuel cells. Again, cell phone backup power, forklift, and stationary power. And there is quite a bit of hydrogen that's already produced in the United States and used in industry. And there is actually some hydrogen pipeline. In that video with the Mirai, you saw it pull up to a fueling station. That's in Torrance, California, and that's off of Air Products hydrogen pipeline that runs. The station basically sits between the production site and a refinery that uses that hydrogen. So they just pull hydrogen off that pipeline for that fueling station. In terms of the transportation application for fuel cells, the Department of Energy has been involved with quite a few projects, racking up millions of miles in travel and many station deployments, so there's a lot of experience in that realm. Overall, again, a very diverse application for hydrogen and fuel cells. They're very scalable. So they can be very small for portable power and very large for primary power and anything in between. So why are we doing hydrogen? Again, it can be produced from local resources. It can be produced renewably. The fuel cell uses it extremely efficiently. So in terms of the amount of energy we need to put on board this unit or in a car, it's less than the conventional fuels. It's got a very good safety record in industry, actually. And if you're interested, there's a database of hydrogen incidents and best practices that I can refer you to. And it is non-polluting. So we don't want a release necessarily, but if it does, it's not going to be detrimental to the environment. As I mentioned a moment ago, the traditional method for hydrogen production and the way they've done it for going on 60 years in industry is by reforming natural gas. And that's a pretty cost-effective method right now. But the research and the drive is towards the renewables, both for the energy that we need to make the fuel and for the source of the fuel itself. Mr. Toyota mentioned that hydrogen can even be made from garbage, and that is essentially true. There was a fueling station in California that was a Department of Energy project that was making hydrogen from wastewater, the digester gases off of wastewater from a water treatment plant at Orange County Sanitation District. Unfortunately, the funding in that project has run out, but it did demonstrate well. So we know that hydrogen's made pretty predominantly, and these are some of the applications in industry, things we might not have thought about, but pretty, standard. And again, petroleum refining is one of the largest uses for hydrogen currently. Because it's made in such quantity, it has to be distributed. We mentioned there's some pipeline. Also, it's shipped as a liquid and as a gas. So the placards, of course, for liquid and gas. These are pressurized tube trailers and low pressure cryogenic tanks. If something's a cryogen, it has to be that cold to be liquid, right? So in this pressurized gaseous tube trailer, is there any liquid phase in there? No, because hydrogen's a gas at ambient temperature and it is a cryogen, so pressurizing it doesn't liquefy it. Making it minus 423 or colder is what liquefies it. So that's something to point out because we are putting pressurized gaseous hydrogen into these tanks to run the fuel cells. So you are familiar with the DOT placards. Again, this is for transport for commerce. So when they're being transported on the road for delivery. I talked about the fact that it's a cryogen and a gas at ambient temperature. The energy content of hydrogen, we talk about hydrogen in kilograms because it is metered by weight, but you can think about it pretty much like a gallon of gas. So if you were to burn a kilogram of hydrogen, which we're not doing, and you burned a gallon of gasoline, you'd get about the same amount of energy out in BTUs, which is British thermal units. It's a standard way of measuring energy output, but the point being that it's about the same energy content. What we're doing in the fuel cell is an electrochemical reaction that's generating electricity. So there's no combustion. But when I say that this unit, again, holds about 75 kilograms of fuel, you can think about that as about 75 gallons of gas. We don't odorize hydrogen. It's a very tiny light molecule, right? What number is it on the periodic table? Go back to chemistry. 1. So it's very small. It's actually very difficult to contain because it's so small and light. And to find an odorant that would stick with it is problematic. But more importantly is that an odorant would be detrimental to the fuel cell itself. The fuel quality requirement for fuel cells is nearly 100% pure hydrogen. So even things like sulfur is a bad one. Water, carbon dioxide, things like that can't be in there. It's got to be almost 100% pure. So an odorant would certainly not lend to that. In terms of, again, the energy, it's more energy by weight and less by volume. That combined with the efficiency of the fuel cell, which is about 60 to 70%, we don't need to put as much energy into the fuel storage to get equivalent or comparable range within the vehicle or use out of the genset as you do with conventional fuel. So we'll talk about how we detect, if there were a leak, how we detect it since there's no odor. Hydrogen's a fuel. You can combust it. It is flammable, and industry recognizes that it has a fairly wide flammability range. The point here is, however, that the hydrogen gas sensors that are employed in vehicles, at fueling stations, in this unit that's being deployed, is that they are calibrated and will alarm at levels that are very conservative and much lower than this lower flammability limit. And actually this 4% is not an absolute number. There's a lot of variables that go into it. And I've been told recently that actually flammability doesn't begin until about 7 or 8%. But suffice it to say that the hydrogen gas sensors will start alarming somewhere in the neighborhood of 0.4% hydrogen and air, and ultimately shut down the system at around half of that LFL. So about 2% in air. The most easily ignited mixture at 29% is quite a bit higher than gasoline vapor or natural gas. But with these trade winds, do you think you're going to get to 29% very easily? Honestly, the industry understands these properties, and so the systems are designed such that between the hydrogen gas sensing and the ventilation, that you're hard-pressed to get anywhere near this 29%. If you do have a hydrogen flame, and we'll see one outside and on video, the internal flame temperature is quite hot. However, there's very low radiant heat. The internal flame, like if you stuck your hand in it, you're going to get burned, but you can get your hand pretty close to it before you feel that heat, because there's no carbon. Carbon's what gives that radiant heat. Nice campfire, nice and hot, burning the wood. No carbon means no or very little radiant heat. So here's an example, and I have a video to show as well, comparing a hydrogen flame in the daylight, this is pure hydrogen, with a propane flame. However, with the thermal imaging camera, or TIC, you can visualize that flame.
This prop provides a side-by-side demonstration of the flame characteristics of hydrogen and propane. It consists of 2 burners fed by 2 cylinders. One cylinder contains gaseous hydrogen, and the other contains liquid propane. The gas pressures and flows have been adjusted to make the flames similar in size. Here we have the propane and hydrogen flames burning on a bright sunny day. The orange propane flame is clearly visible. The hydrogen flame is nearly invisible. But when we look at the flames through a thermal imaging camera, we can see both flames clearly. A pure hydrogen flame has low radiant heat, much less than the amount of heat radiated from the burning of conventional fuels. Because of these characteristics, it is best to approach a hydrogen flame using a thermal imaging camera. Now, let's do the same demonstration in the dark, at night. We are in the same location that we used in the daytime. You can see that the same landmarks are visible. In the dark, both flames are clearly visible without a thermal imaging camera.
I've mentioned that there are a number of different kinds of fuel cells, and it depends on what's in the membrane. We're going to see how the fuel cell works here in just a moment. This is a large stationary fuel cell that's providing power at the Toyota campus in Torrance, California. I have a video on this too, but I'll walk you through it quickly. Hydrogen's brought in from the onboard storage and oxygen from the air. There's a catalyst, which is platinum, in this membrane that catalyzes the hydrogen molecule to split into protons, which pass through the membrane, and electrons, which are routed externally and generate the electrical current. The byproduct of this reaction is water and heat, and it's much less heat than internal combustion. So there is cooling for the fuel cell system in this unit and in cars and things because you do have heat generated, but again, it's much less than internal combustion.
A PEM fuel cell is made of a catalyst-coated membrane between two plates. Hydrogen is fed on one side, oxygen on the other. The hydrogen splits into a proton, which goes through the membrane, and an electron, which is captured as useful electricity. The proton and the electron combine with the oxygen, generating water and heat. A fuel cell will operate continuously as long as fuel is supplied. By combining single cells, a fuel cell stack can be made to produce the required amount of power.
The comment in the video that the fuel cell will generate power as long as it's getting fuel. When the system's shut off, the fuel is isolated to the storage tanks via electrically active solenoids in the tanks. And so the fuel cell is powered down by a number of mechanisms, but including the fact it's no longer receiving fuel. Okay? So while it is a high voltage component, it is not storing charge. Again, if it doesn't get fuel, it won't be producing electricity. So these are the hydrogenics fuel cells that are being put into this unit. There will be 4, and you'll see what the whole module looks like, but these are the individual fuel cells. So let's talk about how we're storing the fuel. I start with the vehicles to, again, give some relativity. It's essentially the same. There are carbon fiber wrapped high-pressure tanks. So the Mirai and the other light-duty vehicles store hydrogen at 70 megapascals or 10,000 psi. And that's really at the level of the tank because the fuel is regulated, the pressure is regulated down to deliver it to the fuel cell stack. It's again stored as a gas. Really the liquid storage is for storing fuel at a fueling station. There's really no vehicles that store liquid right now. Passenger vehicles store a maximum of 6 kilograms and buses about 40 to 50 kilograms. So this maritime application at 75 kilograms is quite a bit larger in terms of the fuel storage, but that's again to get the operating hours that are needed for the unit. And we'll see a diagram of the tank storage system. To illustrate the difference in the carbon fiber thickness between a 35 MPa, so excuse me, I didn't mention, this unit will be storing fuel at 5,000 psi or 35 megapascals. So this diagram is indicating or showing the difference in the thickness of the carbon fiber between those two tank types in terms of the pressure. So these are both a type 3, which is what's on the unit, and it's a aluminum lined tank with the carbon fiber overwrap, and again at 35 MPa or 5,000 psi. Each tank is equipped with a thermally activated pressure relief device. That means that that PRD has to see heat, and there's a fusible plug that will melt open and vent the contents of the tank. So they're not intended to seal back at a certain pressure. Once they're opened, they're venting the contents. In terms of the qualification for these tanks, and this goes for the ones that are in the unit, vehicles, etc., they do go through a series of rigorous testing per batch to qualify them for a lifetime of at least 15 years. And they have a safety rating of a minimum 2.25 times what the service pressure is. So while these tanks are being used at 5,000 psi service pressure, they can actually withstand much higher pressures. These tanks are designed to NGV2, which is also an acceptable vehicle tank standard. And again, all the tests are designed as part of the qualification testing. And the goal is that the tanks vent the contents and we don't have a rupture. Okay? We don't need a ruptured tank. That's not a good thing. So the cylinders being used in this application have gone through a battery of tests. And for example, it's holding 15 tanks, but this batch, they would actually produce 16 and a half because they make an extra tank plus a liner to do these qualification tests. So this is what a computer rendering of what they look like. So again, 15 tanks in the storage unit. These are the high pressure vents. So there are those thermally activated PRDs in the ends of both tanks, as well as the solenoid valves and other equipment for regulating pressure and so forth. So this is again at the end of the tank at the top with a 45-degree angle to facilitate, if there was venting, it would vent up and away, as well as a 45-degree angled roof, because if you did have a leak, then the hydrogen would want to migrate to the highest point and leak out, being so light. Okay? This is also essentially open to air, so there's a lot of passive ventilation in this end of the ISO container. It's not a sealed container on this end. This is the vent for the low pressure line that delivers the hydrogen from the tanks to the fuel cell. So there's also a vent for that line. So again, we're storing almost 75 kilograms of gaseous hydrogen at 5,000 psi. Also, this hydrogen storage is open to atmosphere, and we have that slanted roof. The generator room, which has all of the electronics and so forth, is cut off from the hydrogen supply when the system is not in operation, and is additionally equipped with 2 hydrogen detectors. So should there be a leak, then you would be able to detect that, and the appropriate measures would be taken by the system. That generator room includes the fuel cell system, the ultracapacitor, battery systems with the inverter, and then we have 10 output plugs, and they cite this steel floor as another technical spec. So here's an overall layout, obviously without the walls and ceiling. You'll see that in a moment, where the unit will be fueled. Here's the PRD or vent releases on this end. This is the inverter. This electrical cabinet includes the system controller, batteries, ultracapacitors, and contactors. Here's the user interface with the reefer plugs on the opposite end. So this is really the only place that the users will be interfacing with the unit. Since it'll be fueled by other personnel, that'll happen at this end. And you'll see a man door, so someone can enter this room, but there's really no reason for any of the operators to be entering that space. This is the air intake. So earlier in the presentation, we talked about the 2-foot clearance to allow for adequate air intake so the fuel cell can operate properly. And that's located here. And here's some exhaust and other vents. We'll see a slide later that better points out the hydrogen and smoke detectors. In terms of the codes and standards, specific maritime codes and standards are being developed, but this system was designed using existing codes and standards for the hydrogen piping, electrical, the fuel cell to fuel cell 1 and UL, etc. So if there's any doubt, there's definitely been appropriate consideration in terms of codes and standards. For the system controller, it's the central brains, the central nervous system of the whole thing. It's going to be monitoring all the operation, pressure, all kinds of things. And if it sees a problem, it is designed to shut the whole thing down. In addition, there's an e-stop. There's a couple of them. There's 3 total, and we'll point that out. So if anyone has doubt, hit the e-stop. If you as responders get there, you're not sure if the thing is what the status is, hit the e-stop, and that powers everything down. Smoke and hydrogen detectors. So there is 1 hydrogen sensor in the storage room, kind of a redundant safety factor because you also have that It's open to atmosphere, lots of passive ventilation. And the way it's designed, it also keeps from hydrogen accumulation in this room. In the generator room, we have 2 hydrogen sensors and a smoke detector. There's active ventilation in the storage room. And this wall here separates the storage from the generator room. So in terms of separating these zones, the generator room's relying on the detection and active ventilation for declassification, and the storage room's relying on the open to atmosphere, and as well as that slanted roof that would allow for any leaking hydrogen to vent out. So redundant and multiple safety systems included on the system, or on this unit, include the hydrogen and gas sensors, the e-stops, thermally activated pressure relief devices, 2 per tank. Again, 1 on each end of the tank. So if you had fire on one side or the other, those are designed to vent the contents. Plus a pressure relief on the 100 psi line. Various regulators and control valves, pressure switches, the emergency vent stacks, again, pressure protection on the piping. Upon startup, the system goes through redundant safety checks. If it senses something's wrong, it's not going to complete the startup procedure and completely power up the unit. And then we have the ventilation. All right, some more diagrams for you. We talked about the air intake, exhaust, the vent relief ports here on this end, and they will be orienting the unit such that those are facing out. You'll notice on the hydrogen end, this is all open, and there's splash guard. Another view of the front and back, if you will, user interface plugs, and the vents with the louvered doors. Again, illustrating the rise in the roof there and a common sense approach for natural ventilation should you have a leak in that storage area. Here are the flow restricting orifices to protect against pipe breakage. The solenoids are here, and various other safety systems for the overall hydrogen storage. As I mentioned, there is cooling that's required for the fuel cell, and that's in these takes place with these radiator fans. And that's one thing I need to confirm with the manufacturer. I believe that these are class 1 or class 2 explosion proof, basically, or intrinsic, and I have to confirm that. Because they are on the hydrogen storage side, and that was basically an element of real estate where they could be placed. So they needed that much space for the fans. When the unit's filled, again, this is the fill port here and some mechanical gauges. As we pointed out earlier, a hydrogen sensor in the storage room, 2 in the generator room, along with a smoke detector. There's a stage of the unit, there's on and operating and totally off, and then there's sort of this intermediate phase where they can do a leak check, and that is powering up the sensors with a 24-volt system, but it's sort of an intermediate stage of the unit. And the users don't want to leave that on because it would ultimately drain the 24-volt system if it isn't run and regenerated. Diagramming the hydrogen piping and pressure relief device here in the generator room, redundant safety for that. So we have the fuel cell power module rack is equipped with 2 redundant solenoid valves for the supply. Each rack has an overpressure switch, supply solenoid valve, and pressure transmitter. So again, constantly monitoring pressure and temperature, and if it sees a problem, a sudden drop in pressure or a hydrogen sensor goes off, it will take the appropriate action. Some images or information on the components. This is, I mentioned there's 4 fuel cells, so here they are, and here's the assembly, so the rack that's going in. And that is going to operate the way that you saw in the video. So there's 4 of these power modules, 120 total kilowatts total DC power. There are high voltage lines, of course, associated with this, and I'm told that they will be indicated with orange as to what the high voltage is, where the lines are, those that are visible. An inverter, and there is a user manual that I can make available if there's interest to first responders. Ultracapacitors, so the lines running between the ultracapacitor and the other high voltage components will be, the residual charge will be dissipated on shutdown or if the e-stops hit, but the ultracapacitors will maintain charge and ultimately dissipate charge over a matter of hours. But immediately after it's shut down, they still, of course, can have charge. The lines themselves have been dissipated. 24-volt battery, startup batteries, and also what powers the sensors in that leak check mode, along with the power supply. Just some kind of specs on those. For routine operation, The reefers can be connected to those 10 plugs at any time, but it's not until this green system light is okay and solid green that those reefers will be powered. Okay, so during routine operation, they simply hold the start button, hydrogen and smoke detectors activated, and ventilation system, and then the leak and safety checks are conducted. The minimum action on this step is that there's a trouble that can be cleared by the user. The maximum is that there's a leak detected and shut down. So, and in that case, they need to determine where the leak's coming from, and it wouldn't be operational at that point. And again, any problems, there's the e-stop. On shutdown, you have the power from the inverter is interrupted, the output power. The fuel is isolated into the tanks because those valves that are activated by the 24-volt system and in a closed state normally are shut, so it isolates the fuel. The fuel cell system goes into shutdown, and the residual fuel in that low pressure line that's delivering the hydrogen to the fuel cell stack is purged. So there's no residual fuel in the lines. This whole thing takes about a minute to shut down. During the leak check, the operator will use this system leak check button here and hit start. And there's a series of flashing lights. So we'll have a summary on this, but basically the system OK light will quickly flash, indicating a leak detection check is taking place. If it fails, then the red light will go on and the alarm will sound. Someone can push an e-stop, or if the alarm stops sounding, then that hydrogen level has dropped below a detectable level, and theoretically the hazardous condition has mitigated itself. So, but we still need to figure out where the leak is coming from. Okay. If the user tried to just reset everything, start over, the same thing happens. It's basically not going to start up if it finds that there's a leak. Probably the more likely situation is that it passes, and that green system OK light will then go to a slow flash, and the status of the hydrogen sensors will be continuously monitored during this mode. So they need to stop this and do that by pushing the stop button. So again, they need to stop this action, otherwise that 24-volt system stays powered on. At any point, the e-stop can be hit, and that will completely power down the system. There are three, one on the user interface, which is probably the easiest, and two additional inside the generator room, one on that inverter and an additional one in the generator room. According to the user manual, if there's an audible alarm, a trained responder should be contacted to investigate if the leak has occurred and determine the source of the leak. And that may also probably involve hydrogenics. And we did talk yesterday about the communication tree between Young Brothers, hydrogenics, and first responders, so that's being worked on. A solid red light without an alarm indicates that a non-hazardous fault has occurred. So nothing necessarily dangerous, but there's something wrong, and just the regular stop button can be pushed. So quickly, let's talk about fueling, and then we'll go outside and we'll see the flame prop. Again, this is not, there is the NFPA 472 diamond on here, but this is not being considered a stationary facility. But the hydrogen fueling station would be. So stationary can be bulk storage, fueling stations, or stationary fuel cells. This diamond will be on the one side of the container, and we'll see an image of that later. In terms of the fueling, they're following some of the same protocols and procedures as for vehicle fueling in terms of the type of nozzle and the type of receptacle on the unit. So that would be at 5,000 psi, a nozzle just like this. And the station, when connected to the unit, should perform a series of leak checks as well, and not fuel if it's not connected properly. It is a closed loop fueling, so any leaks, again, would stop fueling, and this is the nozzle that would be used. So the fueling will take place on the storage side, and again, there's some mechanical low and high pressure gauges. In terms of safety systems at the station, you have high pressure storage, so you'd expect to find pressure relief systems. There's also gas sensors employed and flame detectors at the fueling station. Other design elements that you'd expect to see at other fueling stations, including an e-stop there. There's breakaway devices, impact control, and so forth. they do go through safety analysis, just like this unit did. It went through an FMEA before it was built. So just to show you some of the existing stations in California, in addition to Hickam here, there's a handful of stations where customers fuel that have a variety of ways of getting hydrogen. At Hickam, they have an electrolyzer, which is making hydrogen from water, and that's also the case at this station here. You see the solar array. Hickam also has a nice solar array. This station has liquid hydrogen delivered. That's the pipeline. This is the one that was making it from the digester gas off of the wastewater. And this one is steam methane reforming at Newport Beach. So there's Hickam with their solar array. And the dispenser is here. And then all of the fueling production equipment and storage is behind the wall here. The fueling can take place with portable fueling trailers. And this is an example of one. In the case of a station, you would have some intermediate components, but for the potential trailer that would be fueling this, it would have fueling capability right on it. And that trailer is also under development. It would have to hold more hydrogen and be able to fuel the unit. So to have 220 kilogram capacity at about 6,500 psi to do a cascade fuel into the unit for 75 kilograms. Again, they're going to use automotive nozzle and receptacle. And this is early drawings or renderings of what the trailer would look like. And it would be fueled at Hickam and then be potentially brought on site. And the idea now is that the unit will be transported to Hickam Air Force Base to be fueled and brought back, and this trailer could be deployed later in the project.
Everybody, might be a little harder to hear, but the prop you see here was donated by Blue Planet Research, a company on the Big Island. I brought it over here just so we'd have something to show, so that you have a chance to see, like with the thermal imaging cameras and stuff, what a hydrogen burning like in the daylight looks like. So we'll go ahead and light this now. This is essentially just a wok cooker, so there's not much of a flame associated with it, but it allows to demonstrate. And the hydrogen's only at a couple of hundred psi in the tank, so it's not going to produce much either. But it is opportunity to show you there. Okay, so it is burning there. As you can see, it's not very visible. You can see just a few little flecks of color, and that's mainly some impurities that are either in the line or on the burner itself. So in daylight, it's pretty hard to see. But that flame temperature, again, is about 4,000 degrees Fahrenheit, so it's really hot. Very little radiant heat, though, so if there's a jet of it, you can get very close to that, which can be a hazard. You know, there's not a lot of anything to indicate that you're getting into a hydrogen flame there. So, see that pretty well in the thermal imaging cameras?
Yeah.
Okay, good.
So just to review some properties of hydrogen, that we have a light gas that rises and dissipates very quickly. It is a small molecule and difficult to confine, and so ventilation is a primary mitigation factor for accumulation of hydrogen. And we have, again, the open air of the hydrogen storage side of this unit. So if it is released inside, it quickly finds a way out, and it does diffuse through materials as well. So again, 14 times lighter than air. Many of you are familiar, I'm sure, with gasoline vapor being heavier than air. So this is just relating it to some other fuels that you might be more used to dealing with. Auto ignition temperature is quite a bit higher, or at least higher than these other conventional fuels. The flammability range, while we recognize it's very wide, the optimal combustion mixture in air is quite a bit higher, again, than these other fuels. with not a very good chance you're going to get to that given the other elements of the use of hydrogen being in the open air and gas sensors that are calibrated down around this lower flammability limit and even below that. So again, designed to ultimately shut down around 2% and start alarming at levels lower than that. Low radiant heat, as we've talked about, in terms of responders, your thermal imaging cameras can be a useful tool if you suspect that there is flame. Scanning the unit with the TIC could be helpful. A little bit more on the tank testing that happens for qualifying the tanks. Two of the tests include what used to be called the gunfire test is now called a projectile test, and this has been harmonized in the standards across the globe, essentially. And in this situation, the hydrogen tank was filled to pressure at 5,000 psi, and they shoot it at a 45-degree angle here because that causes the most damage to the carbon fiber. And the qualifications in the test actually say that the projectile, in this case the 30 caliber armor-piercing bullet, does not even have to penetrate the tank. But if it does, then the hydrogen has to vent out and not rupture. So that's what's happening here, is there's the tank there and the hydrogen's venting out. Okay? This is not to simulate gunfire per se. In this case, it's to simulate something penetrating the tank at a high impact collision or something like that. Another one of the tests is the bonfire test, which actually starts with a flame impingement test and moves to an engulfing bonfire. I'll remind you that these tanks have thermally activated PRDs on both ends of the tank. So if there's fire on one side or the other, that's the goal, is that the PRD would see that heat and be able to vent. So in this case, they've put a 10,000 psi tank into this oven, and there's the flame there. They have the PRD routed to a vent stack, and it's venting hydrogen. The reason for the steam there is that, or it's actually condensated water. They had a high water content in the hydrogen that day, so it's a side effect. But the point being that it vents the contents of the hydrogen and doesn't rupture as a result of the fire. So in terms of what to do in a response, we are not here to give you tactics. The goal here is to give you information that, as first responders, you can add into your standard operating procedures for responding. And so we've, in this slide session, have adopted sort of the National Fire Academy command sequence, and I'm only going to highlight a few items from this sequence. So in the scene size up, obviously you want to consider or determine if there's hydrogen fuel. If there is there fire, and is it impinging on the tanks? If it is the tank venting? And because these are high pressure tanks, a vent would be a very audible event. You would be able to hear that most definitely, probably before you ever saw anything. So something else to consider is there is really not a way to determine if the tanks have already vented or which tanks have vented. So asking eyewitnesses is one way to determine if venting has occurred. But again, those vents, if you recall the location, are at the highest point on one end and are angled up to facilitate venting upward. So if the tanks are venting, is the hydrogen burning? And because these are high pressure vents, it's possible that you don't see flame until some distance from the actual point of the venting because of the concentration and the velocity of the gas that's escaping. If it's on fire, let it burn itself out. Let the hydrogen vent and burn, because if you do extinguish the venting hydrogen that's ignited, you still have gas venting, and that could reignite and possibly be a worse situation. So as it's burning, it's using itself up, and as soon as that hydrogen's gone, that flame extinguishes itself. And in the meantime, you can be fighting the non-hydrogen fires conventionally. If it's not burning, determine if there are potential ignition sources. Again, Young Brothers will be employing hazardous separation for this unit, even though it's not required, but it will be, have some separation distances applied to it. Can the hydrogen be dispersed to levels below the LFL? When we were here for training with the fuel cell flame prop, if any of you recall, one of the tactics was to employ a 45-degree angle fog spray to divert a hydrogen flame or venting hydrogen. And I would say that that could be a tactic in this case, if need be, to help disperse the hydrogen that's venting. There is high voltage on this system because we have the fuel cells, we have the ultracapacitors and the inverter. And again, those lines will be marked with orange to indicate anything over 60 volts. So there is the high voltage there. However, if we have powered it down via the e-stop or a regular shutdown, that high voltage is interrupted and the residual power in the lines is dissipated. The ultracapacitors will have charge initially on shutdown and will dissipate over time, so over a matter of hours because there's a lot of charge. Okay, so for identification, we've seen a little bit earlier in the presentation, but this is one side of the container. So again, it's a 20-foot container, standard ISO container. It'll be Young Brothers blue, what you've seen outside, and it'll have this decaling indicating it's a hydrogen fuel cell. And it'll have decals for the partnerships and the different organizations here. On the other side, we'll have some of that same decaling, and there you'll find the NFPA 472 diamond for gaseous hydrogen storage. The vents will be indicated with the bright coloring, and here is the location of those hydrogen high pressure vents. There's also indications for the high voltage and so forth in the man door. We don't have liquid storage. We have high pressure cylinder storage. You know, this is sort of the same process as for other stationary facilities. Is there a leak or a flame present? So a gas sensor can be employed as well as the thermal imaging camera. There's no on-site reforming. Presence of other fuels is something to keep in mind because I understand that there are a lot of other fuels that are used and moved around on site. So identifying potential ignition sources is also something to consider when responding to this. As I mentioned, you will absolutely hear a high pressure release of the hydrogen. And these thermally activated pressure relief devices will, you know, a hot day isn't going to make them release, but fire will. And that's part of the testing that they go through. So if the tanks are subjected to fire, and we had some discussion yesterday about, well, if there's a fire that's near to the container, will that do it? I can't say for sure. I can tell you that, you know, if that PRD sees that temperature, then it is designed to open and vent. And otherwise, the goal is to keep the fuel in the tank and maintain it in there, and that's where it belongs. This is just to, again, reinforce that there will be orange, and this is high voltage in the vehicles, but the high voltage will be indicated there. Those lines are designed to dissipate charge, and I don't think there's any reason to be going in there with your cutters, but if you do, just don't cut the high voltage, as hopefully you wouldn't do in other situations. In terms of the trailer that's being planned, it'll be on site temporarily, so it's not a permanent fixture, and be here only for the time to fuel the unit, which would be about an hour or so. But if that was involved, we want to determine, you know, if there's enough personnel to handle both the unit and the trailer, request any additional resources, the same sorts of things that we would employ for the unit in terms of seeing if there's any venting hydrogen, if the tanks themselves are on fire, and so forth. So much of the same tactics there. So with that, there's my contact information, and Monty, if you have any questions or concerns, feel free to reach out. That goes for everybody. We can be your conduit with the project developer and anyone else if need be. But of course, you have Young Brothers here as well that is deploying the unit. That brings us to the end of the presentation, and thank you so much for your time and attention, and best of luck.